Hi guys, it's Mrs. Moss here, and today we're going to learn about how planets move in space. And you may be wondering who this handsome man is on the screen. Well, that's Johann Kepler. And Johann Kepler was a German scientist from the 17th century, and he came up with 3 laws that describe how planets move in space. He was born in 1571 and died 1630. And like I said, he developed these 3 laws. So we're going to talk about the first law. And the first law states planets travel in elliptical orbits with the sun at one focus. So let's break this down a little bit. Elliptical or ellipse is a flattened circle or an oval, and a focus is a fixed point. So what this means is that a planet travels in an oval-shaped orbit around the sun, which is a focus, and that's the shape of the orbit is called an ellipse. Now the sun is not at the center. The sun is off center a little bit. I'll show you a picture of what that means. Make sure you copy this down in your notes. So here's a picture. We have the planet going around the sun. You see the orbit shape is an oval, what we're going to refer to from now on as an ellipse. And the sun, as I said, it's a little off center. It's not right directly in the middle of there's the focus. There is another focus in the planet's orbit, and that's an imaginary spot. So there are 2 foci. An ellipse has 2 foci, the sun and an imaginary spot. That's what gives it that oval shape. A circle only has 1 focus, and it's directly in the center. Like that. Okay, so there's the difference. We have an ellipse with 2 foci and a circle, which is 1 foci. 1 focus. Foci is plural. So we are going to calculate the eccentricity of these orbits. Now, the word eccentricity means how much an ellipse is flattened or elongated, or how far away from being a perfect circle. And so we use the formula that is on your reference table on page 1, so you don't have to memorize it. That is the distance between the foci divided by the length of the major axis. And we're going to go into those vocabulary terms. So an ellipse is a flattened or elongated circle or an oval. The major axis is the length of the ellipse at its widest point. And the distance between the foci is the measurement of space between the 2 foci. So let's look at this a little, get a visual of what we're talking about here. Here is our ellipse. You see the sun is at 1 focus, and the invisible spot is at the 2nd focus. So if we have the distance between the foci over the length of the major axis as our formula, the distance between the foci is that space that we have to measure, and we divide it by the major axis, which is taking the widest part of the ellipse and measuring it through the center of the foci. So if E is equal to 0, it is a circle. And if E is equal to 1, it is a line. Then the value of eccentricity will always be between 1 and 0. The closer it is to 1, the more elongated the circle will be. And I like to remember that because the number 1 is a line. So the larger the eccentricity, the flatter or the more eccentric an ellipse is, then the flatter it will be. As the distance between the foci increases, the eccentricity increases. So let's take a look at this visually. We have 2 ellipses, one with the distance between the foci closer together. You notice that this is a more rounder ellipse, we call this less eccentric because this number, when we do the calculations, the number would be closer to 0, like a circle. If we do the calculations with this one and we see how this space between the the distance between the foci has increased, it's caused a more flattened shape and it is more oval. So we consider that to be more eccentric. This is a diagram of 3 ellipses that start off more round and less eccentric. And as you go to the right, we get more eccentric. The eccentricity increases as that ellipse flattens out. So let's look at this little animation. Oops, we'll go back and see if we can find this animation to show you how it's increasing eccentricity as the space between the foci flatten out. Now remember, there's an imaginary focus right here. So it's the sun at one foci and an imaginary spot in the other. So let's take a look at 3 planets' orbits and see which planet's ellipse is most circular. We would look for the number that's closest to 0, closest to a circle. So planet Y has the planet that's most circular orbit. Taking a look at those same 3 planets, which planet's ellipse would be most eccentric? Now we're going to look for the opposite. We're going to look for the number that's closest to 1 because that's the flatter line. So that's going to be planet Z. You should circle this in your notes if you have a printout of it. And if you don't, you should be copying this down. Okay, so we're going to stop here for right now, and we're going to talk more about Kepler's second law in our next video. I hope you have a great day. Bye.